you very much.
Anytime.
Okay, so I still don't know if we have anybody in Imperial. Pretty sure we're not supposed to have anybody in Valentine today, but we did get the recording up and started. That is a good sign. So let's go ahead and move. Signing in here. Computer. Okay, so hopefully this is recording for us and we'll be able to send this off to everybody. I don't know if 3 hours of recording is going to kill this 2 gigabyte drive of mine or not, but we shall see. If it bugs out on the survey, we'll put another USB drive in there. Okay, so let's get our source all squared away. Let's head off to our website here. Let me go ahead with Internet Explorer and see how that works for us. Okay, U.S. Higher Ed. All right. Let's see, we're going to be doing, we did one-dimensional kinematics and we finished that all up. I believe we're going to be moving on to two-dimensional kinematics. And on here it says that the homework for two-dimensional kinematics would be due on June 1st. When would June 1st be?
Monday.
Next Monday? So that kind of makes sense to us, doesn't it? All right. I don't even know how to check the calendar on this.
There you go.
Yeah, so it would be next Monday. So that makes good sense to us, I think. So that's good. So let's go ahead and see what we've got here in two-dimensional kinematics. We'll discover actually that it's not that much different from one-dimensional kinematics, which is good. So if you remember last time in kinematics, we kind of ended up with solving problems in kinematics, and kind of the way to do this was to start off with a drawing and define all the things we know, then find an equation that fits the things we know with the thing we want to know. And then we can solve the equation for the thing we want to know, plug in all the numbers we do know, get an answer, and be done, which is nice. Pretty straightforward way to solve problems. Gets a little bit tricky, but not too bad. And we did both vertical and horizontal problems. Horizontal problems where we had, like cars accelerating or things like that. Vertical problems where our acceleration was due to gravity. We were doing some kind of free fall problem or some kind of problem where there was no other force on the object we were studying except for gravity. Excuse me. And then here at the end, we talked a little bit about, I'm not even sure if we got to the end here, but we talked about it for sure because we talked about it when we were doing some problems, where the slope of Now the position line, for example, slope of displacement is actually going to give you the velocity, and the y-intercept will give you the initial velocity. And so they give us those definitions here at the end of this chapter, and then you can use graphs to do this kind of a problem. Here you have a displacement graph that is no longer has a constant slope, which tells you that it's probably accelerating, because if it's not a constant slope, slope is changing. If the slope is changing, the velocity is changing. If the velocity is changing, it's accelerating, right? So a curved displacement means that you're going to end up with a velocity that's not a horizontal line, that's not constant, it's changing velocity, and the slope of the velocity line then actually will tell you your acceleration, right? At this point, I usually get the question, well, what if your acceleration is changing? And I say, well, if the acceleration is changing, then your velocity line will be curved, and your acceleration line will no longer be a horizontal line, it will no longer be constant. But we don't generally get much into that in this class because it starts to mess with the mathematics once again. Here we have an example of a jet car displacement. It's obviously the curved graph, right? Obviously the curved graph is going to give us some kind of a slope in our velocity and an acceleration which turns out to be constant, which is nice. And they give us a little picture of it on the next page, which is kind of cool. Jet car. Made lots of jet cars over the years. So here they actually use a graph of a displacement of one of these jet cars to calculate instantaneous velocity at a particular time. And of course, it's going to require that you do a little bit of estimating, and that's what they've got these triangles in here for. And actually, if you've ever taken a calculus course, you'll recognize that they're actually doing something that you do in calculus. It is something that you do. Remember the limits, when you talk about limits, this is what you're doing. Well, of course it makes sense. Calculus was invented by who? It was invented by Newton. It was invented by Isaac Newton, and Isaac Newton invented calculus to do problems like this. Because when he was taking data, he got sloped graphs, and he wanted to know exactly how fast things were moving at different positions in space and time. So the slope of the velocity curve is the acceleration, and so on and so forth. And that takes us essentially to the end of chapter 2, or one-dimensional kinematics. Moving on to chapter 3, we go into two-dimensional kinematics. Great picture here to illustrate one of my favorite physics problems there is, and that is the roller coaster. I love roller coasters. I've always loved them. I've been kind of an aficionado of roller coasters most of my life. I've been on them all over the world, and some of the best ones in the world. There are only a few engineers that design roller coasters in the world. Most of the roller coasters in the world are designed by just a handful of different people. And it's because to get good at this, you really got to be good. To make it not only work, not only make the physics work, but also to make it fun is really difficult. There are a lot of roller coasters out there that are lame, and people that make lame roller coasters don't generally get another job. And this particular roller coaster, I don't even know which one this is, but just from looking at it, I can see this one is the Dragon Con at Spain's Universal Port, Aventura, the adventure port in Spain. This is actually a very famous world park in Europe. It's all designed like a castle. You can see kind of the ramparts of the castle down here. But the designer of this is obviously either the same designer that designed my favorite roller coaster, or learned from this guy. I can't remember his name at the moment, but his first great roller coaster was called the Demon. It was in Northern California where I grew up, and he was the first guy to integrate corkscrews and loops, to go from a loop into a corkscrew was kind of his signature thing that he did. But the thing about these roller coasters is that they're all gravity powered. there are no motors that push the cars on these things. They start at a very high height, and there is a motor that pulls them up to that height. And then everything after that is essentially just gravity pulling these things along. And that's what makes them so amazing. That's what makes the physics so interesting and engineering so challenging. So lots of fun stuff to be doing here. I've had a few students that have been interested in roller coaster design. If you're interested in that kind of thing, mechanical engineering is where it's at. You need to go into mechanical or civil engineering, and you need to go and live in a place that has lots and lots of roller coasters. So more habited areas. There's quite a few roller coaster rich places in the Midwest, but most of them are in places that have really nice climates, so that you can keep them open year round. So California, obviously Arizona is a big place for that, Las Vegas, and then you go into Texas. There's quite a few on the Gulf Coast of Texas, and Florida is just full of them. There's just Orlando, Florida is like roller coaster city. So anyway, one of the coolest jobs on earth, without a doubt. So, kinematics in 2 dimensions. What's this going to mean to us? So, let's start with displacement, right? Our starting point, this is some city with, the standard city block layout. And we're going to start down here in the lower left-hand corner, and that's going to be our 0 point in the X direction, or the east direction as they're showing it here. They're showing both the X direction and Y direction, but they're also showing north, east, west, south, that kind of stuff. So we have 2 things to kind of orient ourselves. But the positive X direction is definitely towards the east. The positive Y direction has definitely been shown towards the north. And that's very commonly done. Not necessary, but it's commonly done that way. Anyway, we start at this starting point at our 0 point on the block. We go 9 blocks east, and then we go 5 blocks north, and that is our destination. However, that is not the whole story as far as our displacement goes. Our displacement is not 9 blocks east, 5 blocks north, because that's going to give us a different distance than would our straight line distance or our actual displacement. Displacement is you can kind of think of it as your distance from starting point to ending point as the crow flies, or whatever, right? So the straightest line between those 2 points. So you're going to just draw this line between your starting point and your ending point, and you're going to get a nice little right triangle here, and that will be your actual displacement. So of course we're going to have to use the Pythagorean theorem. Remember our good old friend Pythagoras from ancient Greece. And the side C, or the hypotenuse of the triangle, I always think the hypotenuse is called the hypotenuse because it's the longest side of the triangle, and it's just a really long word. But anyway, hypotenuse is C equals the square root of the sum of the squares of the other 2 sides, right? So there is the Pythagorean theorem. Sorry, in this particular problem, we're going to have 9 blocks squared plus 5 blocks squared. The 9 blocks squared, of course, will give you 81. The 5 will give you 25. 81 plus 25, you're going to get 106. Square root of 106 turns out to be 10.3. And so you have 10.3 blocks of displacement, approximately. That's not an exact number. The exact number would be the square root of 106. But that is a shorter displacement than the 14 blocks that you actually walked or drove or rode your bike to get there, whatever, right? Whatever your path was. So your path distance is now different than the displacement. Of course, a car can't really travel that distance. You travel through that distance or through that path. A helicopter maybe could, but anyway. At this point, we're going to have to start talking about vectors. Now, in the lab that I gave you for this past week, and the week before, they talk a little bit about vectors and how the length of an arrow can represent the strength of the vector or the or how much the vector, they call that the magnitude in physics. So if you have a displacement vector in the east direction, then the length of this in the east direction tells you how far you went, and the arrow shows you which way you went. Of course, the hypotenuse of this triangle is not pointing in the east direction, it's pointing kind of northeast. And so, but still, it's the same deal. The length of it tells you how far, how much that displacement is, and the arrow tells you which direction that displacement is, right? However, these two vectors, the 9 blocks to the east and the 5 blocks to the north, combine to give us enough information to give us that hypotenuse. We use the Pythagorean theorem and we can get the other vector. We can even use a little bit of trigonometry and calculate the angle, which happens to be 29.1 degrees. How do you calculate that angle? Well, you can take the inverse tangent of the 5 blocks north over the 9 blocks east, because the tangent of this angle will be the opposite side over the adjacent side. If you don't remember that, you can maybe go back and review. A lot of people like to use the word SOHCAHTOA, S-O-H-C-A-H-T-O-H, to remember the T-O-A, to remember that, where it's S-O-A stands for sine opposite hypotenuse. So the sine is equal, the sine of an angle, theta, is equal to the opposite side of the triangle from that angle over the hypotenuse of that triangle. The cosine of that angle is equal to the adjacent side of that triangle over the hypotenuse of the triangle. And the tangent of that angle is equal to the opposite side over the adjacent side. If you remember that SOHCAHTOA thing, that's kind of helpful. I actually never even heard of that until I was teaching college. It was something I'd never learned, so probably just wasn't listening in high school. But anyway, so a little bit of trigonometry here. We can get the angle, a little bit of Pythagoras, and we can get the hypotenuse side or any of the other sides if we have two of the sides, and we can get information from this. So we start to think, well, even though these two vectors, the eastward vector and the northward vector, even though those weren't the actual displacement vector for this particular movement from the starting point to the ending point, they're still useful to us. And so we're going to give them names. We're going to call this one that's going to the horizontal direction or the x direction, we're going to call that the x component of our displacement vector. And this one that goes to the north, we're going to call it the y component of our displacement vector. So it's like the two parts that make up, if we use the right math, they can make up all the information for the actual displacement vector, which is the hypotenuse of that triangle. And so we're going to start thinking in terms of that since we're in two dimensions. Why is it that we can do that? The reason that we can do that is actually shown here, or is actually demonstrated here in this little drawing. In this drawing we have two balls, one that is being dropped straight down, and one that is being thrown horizontally and also drops at the same time straight down. Well, it doesn't drop straight down, it drops kind of at an angle because it's dropping as it's being thrown forward. But it's being thrown exactly horizontally forward. And if you do this experiment, you will find that this will always happen. The ball that is dropped straight down and the ball that is thrown forward perfectly horizontally and still falls down will both land at the same time. In fact, their vertical motion will be the exact same. And that's because the acceleration in the vertical direction is the same on both balls. And what this illustrates is that vertical and horizontal motion are independent of each other. That each ball doesn't care what's happening in the horizontal direction as far as their vertical motion is concerned. The vertical acceleration due to gravity doesn't affect the horizontal motion at all. It kind of makes sense to us when we think about it. But it turns out to be a very powerful mathematical observation for us. This gives us what we call separability in the calculus and in any of the math, actually. What it's telling us, what this observation tells us, is that everything that happens in the horizontal direction can be treated completely separately in the math from everything that happens in the vertical direction. And that separability saves our bacon mathematically. We are now going to give you all you need to know for two-dimensional kinematics. And guess what? It's everything you needed to know for one-dimensional kinematics. You just do it in one dimension, and then you do it in the other dimension. You do them separately, and the only thing that connects the two is the time that it takes for the movement, because the time is not dependent on direction. So let's see if we can get this thing to work here. I have my doubts. We'll try anyway.
Gotta put the yellow box in the
Let's see if we have Java working on this computer. No. No, it does. Running security scan. Yeah, it doesn't know what to do with it. Can't run Java. All right. Next time we'll have the tech people come in and connect my computer so that we can show those things. But what it's all that it did there, all that it wanted to do there, wanted to show us there, is the two-dimensional motion of anything. They're using a ladybug, and how the vectors for displacement, the vectors for velocity, the vectors for acceleration are independent of each other. Again, you can actually see this just in a more static version in this problem here, in this situation here, where the blue ball, which is being thrown forward, falls at the same rate as the red ball. And most people really have a hard time believing that this is actually true in certain situations. For example, one of my favorite questions to give to a student is a hunter fires a bullet from a gun perfectly horizontally to the ground. So the bullet comes out of the gun, it has no rise on it or no fall on it when it comes out of the gun, right when it's coming out of the barrel. It's moving perfectly horizontally to the ground. How long does the bullet stay in the air? And I give them 1 second, 5 seconds, 10 seconds, 25 seconds, or something like this. And invariably, the vast majority of students will choose 10 seconds, or even 5 seconds, or 100 seconds, or whatever. It's a long time. It's, bullets travel forever, because I've seen it in the movies. Somebody shoots a bullet, and you wait, and then it hits somebody far away. Well, no. How long is it? Well, you take your keys or whatever, and you hold them about, the height that you would hold a gun, you drop them, it takes about a second. And that's how long the bullet's in the air. After a second, a bullet that's fired perfectly horizontally to the ground will hit the ground. And anybody who's actually shot guns long distance knows this. Because it doesn't take a bullet long to hit a target. You pull a trigger and it hits the target almost instantaneously, it seems, to your ears. Even if you're shooting 300 yards or 500 yards away, it's like boom, cut. I mean, it hits that fast at 500 yards. Unless you have a very low velocity round. But anyway, it's still not going to be 10 seconds. And the rifles that you generally shoot do not shoot horizontally to the ground. Rifles are actually designed, the rifle sights are designed so that the barrel is shooting upward slightly, so that it has ballistics that allow the bullet to go a little bit further. So your standard rifle is designed it's designed to hit a target at usually about 25 meters and about 100 meters, so that it has this arcing curve that it goes through, hits the target at 25, and then it goes above that, and it falls back down to it again at 100. But still, it's not much more than a second, because the top of that arc is only about 8 feet high. So dropping keys from 8 feet to 6 feet doesn't make much difference. So a bullet doesn't stay in the air very long at all unless you shoot it upward. So that's a very important thing to remember as you're doing these problems, that this separability between the horizontal direction and the vertical direction teaches us that any two directions that are 90 degrees from each other are always going to be independent. It doesn't just have to be up and down, side to side kind of. It doesn't have to be up and down and forward kind of motion like the bullet problem. It will work with any directions that are 90 degrees from each other. If we look at this map here, we have, of course, this is Hawaii, and this is the Big Island, and this is Maui up here, so obviously this is oriented so north. is up this way, since the big island is at the bottom of the chain, and Maui is the next one up. But anyway, so obviously north is up, and then that makes east to the right in this particular picture. And all of our directions that are 90 degrees to each other will be completely independent. You notice that none of these movements, this plane or whatever it is that's traveling, looks like a plane because it's actually traveling on the island, and then it travels across the island, travels across the little place here. But anyway, so this plane doesn't have any paths that are 90 degrees from each other. No two paths have a 90-degree angle between them, which means that there are no two paths here that are completely independent of each other as far as their motion and the mathematics of their motion. However, if we split these directions into a west direction or an east direction and a north-south direction, then we could do this, right? So for example, I'm going to try to zoom in here if I can remember how to zoom in on
That big A.
Let's see on there. That's good. Okay. So I'm going to look at just one part of this path. Here. This is the side of Hawaii that almost nobody goes to. If you want a great time in Hawaii, go to this side of the big island of Hawaii. It's great times. Oh wait, no, I'm thinking the other way, the other side. Everybody always goes to the volcanoes. It's this side nobody goes to. But anyway, it's a cool place to go, the Big Island. Ooh, that's not where Honolulu is. Let's just look at this second part of the path here that goes right here to right here, between these two white dots here. And you can see that it's kind of a little bit north, a little bit east, and so how would we describe this direction? Well, of course, we could get a little protractor and measure the angle from the west direction, or angle from the east direction, or the angle from the north direction. But we could also just draw in our east and west line here, and our north and south line up and down here. Essentially put a little axis there so that we can see where it is. And then we could draw a vector that just shows the western part of this motion right there. Just a little piece there. I'm going to try to zoom in a little bit more even. Oops, guess I ran out of zoom power. Doesn't want to let me. Okay, fine. So anyway, excuse me. If I drew a vector here going east, that would represent how far east I go when I travel this little path here. It would look like a little vector that started here at this dot, came out to about right here, directly under this dot here. So you can see that it would be a little tiny vector pointing off to the right. And then if I went from there to draw a vector that went north, how far I would go for this little part of the trip, it would go from this point and up to here. Or you could draw it over at this point up to here, right? And those would be the two components of my vector, right? And then with those components, we could do the exact same thing that we did on that previous example. Let's zoom down again. Okay. So then I could use those vectors in the same way I did in the previous example to calculate the overall displacement, to calculate the angle at which I'm traveling, and so on and so forth. Just like with the 9 blocks east and the 5 blocks north problem. Here they're showing that again and how that can be used. Here's our 9 blocks east vector, here's our 5 blocks north vector. Those are the components of this overall vector, or the real vector we're interested in, this displacement vector. Now this can be done also with what we call vector algebra, or vector, not vector algebra, vector arithmetic is what we call this. It's adding vectors, right? If you put the first vector, which is that eastward 9-block vector, or whatever it was, and you put it on, the eastward direction, it's already pointing east, but you just lay it down here. And then you take that northward vector and you put the tail of it on the tip of the eastward 9-block vector. You have 5 blocks up. You can see that adding the vectors graphically gives you that hypotenuse, right? And so you can actually physically just stack them on, head to tail to add them together. And in fact, you can even subtract them. To subtract the two vectors, you have to be careful that the first one always goes first, so we put this vector on here, just like we did. And if we wanted to subtract this 5-block vector instead of add it, well, we would just turn it over, because that's like adding a negative, right? So we'd make this into a negative vector. How do you turn a vector into a negative? You just put the arrow on the other side. And so this one would be, the arrow would be on the other side, and we would go down this way. And so if we subtracted these two vectors, the resulting vector would be downward this way, right? And so you can actually add and subtract vectors graphically, and that's what we're going to do in this next example. We have a person who walks the three paths on a flat field. She walks 25 meters in a direction 49 degrees north of east. So here's our first one, 49 degrees north of east, 25 meters. Then she goes 23 meters on a heading 15 degrees north of east. So here's our second vector, 15 degrees north of east. And our third vector is, and then how are we going to figure out where she ends up? Well, we're going to add these three vectors together. It turns out when you're adding vectors, it doesn't matter which order you do it in. When you're subtracting, it does, just like in real life. Right? So we add A plus B plus C, head to tail, head to tail, head to tail. And it turns out that she's out here, just south of east, right? So she could have just gone this distance, whatever it is, and just a little bit south of east and gotten there quicker. Well, depending on what was in her way, there might be a building in the way, right? But to figure that out mathematically, which you can do, you'd have to do each triangle separately and figure out where it ends up. Or you could just measure it with a ruler, because these you've all measured with rulers very carefully, and you would end up with 50 meters, right? Why is that impractical? Because who has a 50-meter ruler? And who wants to go lay out those vectors on a huge field, right? It's not very practical, but it's a good thing to think about, because sometimes it's helpful to think in those ways in order to understand the vectors. Here they have the same problem done in a different order. They add the last one first, C plus A plus B, and you can see that it doesn't change anything. The overall result is the same, even though the path looks different. Here they show us how you make a negative into a vector into a negative vector. It's still pointing at the same angle, it's just pointing in the opposite direction. So it's still, the orientation of the vector is the same, just the direction of it pointing downward to the left instead of up to the right. So here's another example. A woman sailing a boat at night is following directions to a dock. The instructions read, first sail 25 meters in the direction 60 degrees of north of east from her current location, then travel 30 meters in the direction 112 north of east, or 22 degrees west of north. If the woman makes a mistake and travels in the opposite direction for a second leg of the trip, where will she end up? Compare this location with the location of the dock. So here's the first one you're supposed to do. Here's the second one that you're supposed to do. We're supposed to figure out what happens if she travels instead of this way, opposite direction, right? Let's see, is that north? Yeah, okay, so that's correct. So here is the representation of the minus vector where we're going the opposite direction. So instead of adding these vectors, it's like we'll subtract these vectors. And where does she end up? Where does she end up turning up? Well, of course, they're doing this by just putting these things in here and then measuring, you can actually measure that. If this one is a certain length, if this one's a certain length, you can use a ruler to actually measure that. But you can also do the math. And that's what we're going to do down here. We're actually going to do the math. So in this case, I assume they're doing the math. Doesn't look like they're actually doing the math. Well, anyway, if you wanted to do the math of this problem, you could do it. It's a trigonometry trick or equation that maybe you've forgotten, but remember there are more equations than just the Pythagorean theorem and the sine, cosine, tangent in trigonometry. And two of those equations that can be quite helpful in physics are the law of sines and the law of cosines. So with the law of sines, if you know two sides and an angle, you can get everything else, right? Let's see, is that right? Or two angles and a side. If you know, you have to either know two angles and a side or two sides and an angle, right? If you know those three things, let's see. Let's see, if you know an angle and two sides, and an angle. However, the angle has to be opposite one of the sides, right? Whatever you know, if one of the angles that you know is opposite one of the sides you know, then you can use the law of sines, I believe. If you don't have that situation, then you can use the law of cosines to figure everything out, if that's correct, if I remember that correctly. And I've memorized the law of sines. It's always the opposite angle to a side over the side equals the opposite angle to a side over a side equals the opposite angle to a side over a side, right? That's the law of sines. If you don't remember that, go look it up, Google it or whatever, and remember how to use it. Law of cosines I can never remember. It's an equation that looks kind of quadratic and funky. That's all I can remember about it. So time to time in this class. Not a lot, but from time to time. Now, what if we have a vector and we actually want to make the components from the vector? Because why would we want to do that? Well, because we've already told ourselves that the things that happen in directions that are 90 degrees to each other are independent. So it makes sense to us that if we can break all of our vectors into components that are 90 degrees from each other, then we can do the math easy. That's really the next step. That's kind of the obvious next step to go to. So we're going to have to figure out how to take every and any vector we have and break it into two other vectors that still have all that information, but those two other vectors are 90 degrees from each other. And we might as well choose them in the x and y directions, since every vector is going to use the same component system or the same coordinate system, so that all the vectors that we have will all be 90 degrees from each other or lined up with each other. It's a great thing. So we're going to start by practicing with this vector A. We have this vector A, it's pointing up and to the right at some angle theta, and we know, of course, that A, the length of A, which we're going to represent just by the letter A without any kind of symbol on it, the capital letter A, the length of the vector A here is going to be equal to, that's not correct. The bold letter A is what we're going to call the vector. And so if you take the vector A sub x, which is the component of A in the x direction, that's how much A goes in the x direction and the direction it goes. And then you take A sub y, and they're both bold-faced, and so those are actual vectors. And that's the symbolism we're going to use in this book for vectors. Other books put little arrows over the top. We're just going to use bold-faced for vectors. And if it says sub x sub y, you know those are in the x and y directions. They're components. So if you take that A sub x and you add it to that A sub y, graphically vector addition here, then you get the vector A. However, that's not what the length of vector A is. The length of vector, you have to use Pythagorean's theorem. And the length, when we do the length, we will use non-boldface. And you will see that here in a second. Here they show you that these two vectors don't add together to be what we think they might. 3 meters plus 4 meters does not equal 5 meters, for example, but A is 5 meters long, right? How do we know it? Because of the Pythagorean theorem. And so we start using a different notation. For the lengths of each of those vectors, a sub x without the boldface is the length. A sub y is the length. We're going to call it the magnitude, which for a displacement vector is the length, but for a velocity vector that would be like the speed, right? And how are we going to determine it? Well, it's going to be our calculus. Or not our calculus, our trigonometry, right? A sub x is this x component, which is the side adjacent to the angle theta. The side adjacent to the angle theta will have a formula that will give us this. Because if we rearrange this formula, you get the cosine of theta is equal to the adjacent side, which is a sub x, over the hypotenuse, which is a. Right? So that is the formula for a sub x. You take the length of the vector a, and you multiply it by the cosine of the angle theta. And you're good to go. For a sub y, it's just a sine theta. And you're good to go. Because it's the opposite side. Now, if this stuff isn't making sense to you, tell me now, because we need to make sure this is making sense, because we're going to use this a lot from here on out. Anybody having trouble with understanding resolving these vectors? It makes sense?
Yeah.
Okay.
I added it up.
So, here's kind of bad. They've squared the sub number and the sub x and the sub y when they should have squared the a. It's just a typing error, and you can fix that. But that's just Pythagorean's theorem. To calculate the angle theta, you just take the inverse tangent of a sub y over a sub x, and you're good to go. And here they have it all put onto the actual drawing of the vectors, so you can differentiate there and kind of see what's going on, how that's been done. So how are we going to do this addition now that we're not just putting them head to tail and measuring? Well, it turns out that the way that we're doing it is maybe a little bit more mathematically taxing, but it's a lot easier to actually get the right number. So we're going to use up a little paper, but we'll just waste paper. Don't worry about that. We're good with that. And let's see how it's done. We're going to add these two vectors together by breaking each of these vectors into their components. And you can see that the A component has this red a sub x dotted line component down at the bottom, and this red a sub y component over off the left. And the B vector also has components to it, the blue b sub x and the blue b sub y. The b sub x down here on the right, as to the right of the a sub x vector, and it shows how far the b vector goes to the right. The b sub y vector shows us how far the b vector goes upward in the y direction. And those are all our components, and adding a and b together are going to just be like adding a sub y to b sub y, a sub x to b sub x, and making a new set of components for this resultant vector r, which will be the sum of the two vectors. So these two added together will be the y component for this black vector r, and these two, a sub x and b sub x, will be the x component for the r vector, the overall vector. And you can kind of see how that works. This is how far the r vector goes to the right. This is how far the r vector goes upward. Well, adding them together is simple once you split them into x and y, because the x components just add like normal adding. Once you've got the x components and you know what those numbers are, you just add them together to get a new component. Same thing with the y components. And that's what they're doing here. This overall black vector, this overall black vector here are just the sums of those components. The math, not that much harder, because all you're doing is using the formulas, which are right, let's see, where did they put them? Right where, they didn't write in the formulas actually. But you're using the formula from the previous page. Let's go back to it. Using the formulas for a sub x and a sub y, you're using those for a, but you're also using them for b in the next problem. And that a sub x formula was actually on the previous page still. No, it's right here. Is that what you were saying?
No, I think I would fill that in.
Oh, it's right here down at the bottom of the page in step 1. A sub x equals a cosine theta. So the length of a, which is the hypotenuse of this first triangle A, right? You use the length of a times the cosine of theta, and then the length of a times the sine of theta, and you do the same thing for b, right? So you're essentially splitting this into two right triangle problems. This right triangle and this right triangle up here. And you find these sides by using the a sub x equals a cosine theta, a sub y equals a sine theta. So let's actually do one of these problems with numbers. We're going to do the same, we're going to use the same vectors in the figure we were just looking at. We're going to add them together, but they're going to tell us that vector A is going to be 53 meters long in 20-degree direction. So they've told us what the angle theta is, and they've told us what the length of vector A is. The length of vector B is 34 meters, and its direction is 63 degrees north of east. So we know the angles, we know the lengths, we know what we need to know. To calculate these, or to represent these things on the graph, we draw like this. We have our 20-degree angle here for theta of A, and then the length of A here is written as 53 meters. The angle of B is 63 degrees, the length of B 34 meters, written right here. So they've also calculated the angle here. Turns out we're not going to need it, but that's fine. So the first thing to do is to break this thing into its components. Let's write out the components for a sub x, for the a vector, a sub x, starting with a sub x. So a sub x is going to equal a times the cosine theta sub a. Well, the length of a is 53 meters. They gave us that number. Cosine of theta sub a, well, the cosine of theta sub a is the cosine of 20 degrees. We plug in our numbers, we get, turns out, 49.8 meters. Does it make sense? Well, this length right here, which would be a sub x, is a little bit less than this one. So that makes sense, because this one was 53, ours is 49. So that makes sense. That's a good one. Good idea. This next one is going to be shorter, though, quite a bit shorter. It's pointing upward, and it's quite a bit shorter than a, probably about half or less than half of a. So let's go see what it's going to give us. If we skip this next one and go to a sub y, let's see what it gives us. A times sine theta a is again 53 meters, but now it's sine of 20 degrees instead of cosine of 20 degrees. And this is our y component for a, ends up being 53 times 0.342 meters, and that's 18.1 meters, so it's less than half. It's about a third almost, right? So now we've got our a vector split into two components. One that's 18.1 meters long pointing up. The first one, a sub x, is 49.8 meters pointing to the right. We have the components of a sub x and a sub y. You do the same thing for b, but you're of course plugging in 34 meters and 63 degrees, different angles. For the x component, we get 15.4 meters. For the y component, we get 30.3 meters. Now that we know these things, we can actually calculate the length of the vector, the overall resultant vector. How do we do it? We just add them together. We add the 49.8 for the a sub x and the 15.4 for the b sub x. We get 1.5 times as far to the right as it is going up. But to find the actual length of that vector, we take those two displacements, or those two components, one in the x direction, one in the y direction, square them, add them to each other, and then take the square root, and we get a length of our final vector is going to be 81.2 meters. To find the angle that this vector goes off at, we take theta equals tangent -1 of r sub y over r sub x. The r sub y is the 48.4, the r sub x is 65.2. Take that ratio, calculate it using your calculator, the inverse tangent, you get 36.6 degrees. And that's the angle that we have all the way across here. From the x angle up all the way up to here, 36.6 degrees. And now you have all the information for that final vector. You know its length and the direction that it points in. Now, it's nearly 5 o'clock. I'm gonna need to take a short break just to get a drink here in a few minutes and try to decide when to do that. Let's see, how many pages do we have left here? Did I just hear somebody come in Imperial? I can almost hear somebody. Hello? Must have been dreaming. Still can't see anybody out there.
That door's open.
Okay, so yeah, I get the feeling we're not going to quite finish this, especially with our late start, but we'll do as much as we can. And we'll finish it on Monday if we have to. That's not a problem. We can do that. We were ahead for a little bit, right? We were ahead for about a day. Now we're going to have to struggle to stay on top of things. Okay, I will not take a break just for the interest, in the interest of getting this as much done as we can, and much of this material. Projectile motion. So projectile motion is going to be the motion of an object that is only being acted on by gravity. It may have some initial velocity given to it before we are interested in the problem. For example, a cannon may fire a cannonball, but we're only interested in the cannonball after it leaves the cannon, because after it leaves the cannon, there's no expanding gases pushing it on it anymore. The only thing that's pulling on it is going to be gravity. So we will, excuse me, we will be doing projectile motion for quite a bit here. Because, oh, and also the other thing about projectile motion is it can be two-dimensional. So it's not going to be just something that goes straight up and straight down, although that is projectile motion. We're going to add in the possibility of it moving sideways while it's moving straight up and straight down. But of course, we're not going to be too excited about that because we know that the sideways motion and the vertical motion can be treated separately. If we can just resolve every vector in every situation into its y components and its x components, then we should be good to go as far as the math is concerned. But resolving everything is going to be really the work that we have to do here. There will be some situations where we're going to be interested in calculating time in the projectile motion. We do need to realize that time is the only thing that is not separable from each dimension. It's always the same in both dimensions. So at 10 seconds in one dimension, the ball can't be in a different place than it is in the other dimension. They're always in the same place. It ties these two things together. That's a good thing, it turns out, not a bad thing, because it's going to help us to solve a lot of problems. We're also going to assume that air resistance is negligible in all of our problems. And here we get a new set of equations for the kinematic equations, well, a new showing of them. But here we're showing them all in the x direction. And it turns out that's perfectly fine. In the x direction, these equations work perfectly well. But remember, the y direction is equally important to us, and so we have to also use these equations. We have two sets of equations. They're identical, except one of them has x's in it, one of them has y's in it. And also the x direction has an a for the acceleration, whereas the y direction has a g, because we're going to assume the only acceleration in the y direction in most of our problems will be g. We will get to a point at some place in this class where we're firing rockets, so there will be acceleration in the y direction other than gravity. We'll have to deal with that later differently. But for right now, we're going to try to avoid that. Problem solving for this, same as before, except we're going to want to, when we start the problem, instead of just jumping into the kinematic equations, we're going to want to split the problem into two problems. One that uses the kinematic equations in x, with the x components of our vectors. One that uses the kinematic equations in y, with the y components of our vectors. So that's going to be the big difference. Here they have a nice couple of pictures that show the different components, the vector components of velocity for an object that is in projectile motion, where the y is here on the y-axis, of course, the x is over here on the x-axis, and you have this cannonball or whatever it is flying through the air, and it has sometimes velocity components up, sometimes velocity components down, and they're changing length. At first they're big, at the end they're big, in the middle they're kind of small as this thing's stopping and turning around. But the forward component, notice, always stays the same, because there's no air resistance to slow it down, and it's not affected by the upward downward motion at all. It just stays the same, keeps going forward, keeps going forward, and it would continue to keep going forward forever if it didn't hit the ground or something else. So let's look at a real example of this, example 3.4. Fireworks projectile explodes high and away. So we have a shell that's shot in the air with an initial speed of 70 meters per second at an angle of 75 degrees above the horizontal. It's illustrated in figure 3.39. Let's take a look at that. Where'd it go? There it is. Figure 3.39. So the initial speed, initial angle are given 75 degrees, and they give us this initial speed. And then, initial speed, which whatever it was, initial angle 75 degrees, initial speed of 70 meters per second. Okay, so the fuse is timed to ignite the shell just as it reaches its highest point above the ground. So just as it gets to the top of its motion, it explodes. They want us to calculate the height which the shell explodes. They want us to calculate how much time passed between the launch of the shell and the explosion. And they want us to calculate the horizontal displacement of the shell when it explodes. Okay? So they want us to know how long it takes. They want us to know the height it takes to get there, and then how long it takes to get there. And then they want us to calculate how far it goes in the horizontal direction, right? Of course, here they put in the numbers for us early, but we're going to figure out how to actually calculate those numbers. So the first thing we're going to do is hopefully realize that in the y direction, that's where we're going to get our height, right? It's asking for maximum height. That's obviously a y direction problem. What do we know about the y direction in this problem? Well, they've told us the initial velocity, but they told us the initial velocity at an angle, not in the y direction. But we can resolve that to the y direction. We can actually create a vector for the initial velocity in the y direction from this vector using our trigonometry. We can do the same thing for the x direction. First we'll start with the y direction. So the velocity initial in the y direction is going to equal the velocity initial of the shell, which is the 70 meters per second, times the sine of the angle 75 degrees. Plug those numbers in. The upward velocity component, how fast it's moving upward at the start of this problem, straight upward, is 67.6 meters per second. Slightly less than the 70, but that would be expected because some of the velocity is forward. Not all of it is upward, some of it is forward. So we calculate that and we're good to go. We have 67.6 meters per second squared. However, that's not the whole story, because up here we actually have an equation that will tell us what is the total height we're going to reach, G2, if we start at a particular height and go with a particular velocity. Now this equation, they're not actually showing you which one this is, but it is one of the equations from our, let me go show you which one it is. It's this one right here. So your initial velocity right here, which is that 70 meters per second times the sine, right? This initial in the y direction, 70 meters per second times the sine of the 75 degrees gets squared. But on the final velocity, why do we put a 0 there? Well, because it's at the top of the motion. The top of the motion, the velocity in the y direction is 0 because it stops going up, turns around and starts going down. And when you go from up to down, you have to stop in the up and down direction. So that becomes 0. This becomes the 75 times sine whatever it was squared, which ended up being 60 something. And then we're going to subtract 2 times g times the change in distance, and the change in distance in the y direction is the thing we're interested in. So that's why this equation looks like it does, because they've already plugged the numbers into it. And on here they show us the equation. I didn't see that they showed it to us. But now that they plugged the 0 in on the left-hand side, and they've plugged in 0 for the initial position on the right-hand side, and y gives you the final position, then all you have to do is solve for y. Turns out you just have the square of the velocity that we just calculated, 60 whatever it was, divided by 2 times 9.8, which is the acceleration due to gravity. Here you see those numbers plugged in, and you get a height in the y direction of 233 meters. That's good, because when those things explode, they're loud and they're dangerous, so you want to be pretty high. So 233 meters up, and that's in the y direction. Y equals 233 meters. Now, how are we going to use that to figure out time? Well, of course, there's an equation for time. If you know the initial velocity, which we do, if you know the final position, which we do, and if you know the initial position, or sorry, this is final position, this is the initial velocity, final velocity. So, but anyway, if you know all these things, you can get there, and we do know all these things. This equation comes from, they have it right here actually. Y equals initial, so your position, your final position equals your initial position plus 1/2 times the sum of your velocities times those things, and then we know, and solve for t. Right? We solve for t first, get 2y over the sum of the velocities, and then you plug in the numbers that we have, and you end up with 6.9 seconds before it explodes. Because air resistance is negligible, then this isn't going to slow down in the y direction and the x direction at all. So the acceleration in the x direction is 0, which makes a lot of things pretty easy in the equations. And it turns out that we can actually calculate its position in the x direction very, very quickly. It's going to be v sub x, well, that one comes from actually the initial conditions that they gave us. V sub x equals v0 times cosine theta 0. v0, of course, is the initial velocity that they gave us. That's the 70 meters per second times the cosine of the angle 75. We get 18.1 meters per second. It's not moving to the right very fast. But once we have that, then we can use the equations that we've been using all along to calculate, for example, your final position. Final position can be calculated from here. Initial position is 0, so it just ends up being velocity in the x direction times time. We know the time from the previous part of the problem. Time came from the y part, but it's still valid here, so we just plug in that same time. 6.9 seconds goes in for the time. Where did it go? Right there. 18.1 meters per second times 6.9 seconds. So it moves 125 meters horizontally. So even though it's a little bit more work because you have to resolve all the vectors into their components and then split those components onto the x side or the y side on your paper maybe, or in your mind or whatever, I would actually split them on paper. And then you write down equations both in the x and the y direction to try to get your results. Then you'll find it's not that hard intellectually. The big key to this though is to, if you need the time, get it from the y direction is usually your best place because you have the acceleration in that direction. And so it usually gives you a chance to buy that, to get that that resolved. I was going to say to buy that vowel, but I was thinking of a word that was equivalent to that in physics, but it's just not working for me. Anyway, to get that to work, you have to kind of work this problem simultaneously, but also to remember that your time is most likely to come from your y, from all the y numbers you have, the y components and the y equations, because of its relationship, because it has that acceleration due to gravity. Really, you have more options in your equations to use. Hot rock projectile out of a volcano, same kind of idea. They give you initial speed at an initial angle, and then as rock strikes the side of the volcano 20 meters lower than the starting point. Calculate the time it takes the rock to follow this path. Here's the picture that they show, and you can see kind of what's going on here, but it turns out that the math doesn't care that the rock fell below its original starting point. The math will still do it. All you need to know is that initial velocity in the x direction, initial velocity in the y direction, initial position. You need to define it. And that's what they do here. They define its initial position when it gets blown out of the mountain as 0, and the position that it falls to as lower than 0, negative 20 meters below 0, right? But you just resolve the vectors and do the math again, and it will figure it out. And the math does the work. And you can see here they've got an equation for y. They start resolving into y. They do the same thing for x, and they start resolving for everything. They've solved for y in the end. Once they've solved for y, they go back to the x part, and they're good to go. And it's the same kind of problem. Here we see something quite interesting, which is nice. It's a kind of a... I told you earlier that the ballistics on a gun are designed to hit the target at 25 meters and 100 meters usually. And that actually comes from this idea, where if you point something upward at an angle and then fire it, there are actually 2 angles that will get you to that same spot. Here you can see that 15 degrees takes you at a fairly shallow path from left to right, and it lands you at this dotted line in the middle of the purple path. But 75 degrees will get to the same place. It just goes way up high and then it goes back down again. And these equivalent paths in ballistic models are used all the time in lots of places. If you've ever played golf, for example, golfers use this. If a golfer wants to get under the wind, then they use a club to hit that 15-degree path. And they kind of bounce it low underneath the wind. However, if they want to get over a tree, they use the one that goes up high. They use that chipping wedge or the sand wedge or something like that, and they hit it way up high. They also use those same things to keep the ball from rolling, because at the lower angle path, when you hit, you have a lot of forward velocity. Whereas if you hit it straight up, you have very little forward velocity. So the chipping wedge, the pitching wedge, chipping wedge, whatever you want to call it, the sand wedge, all of those are designed to give the ball very little forward velocity and actually give it backspin as well, so that when the ball hits, it rolls forward little or none at all. Whereas your low number irons and your fairway woods and your driver, they're all designed to give the ball lots of forward velocity to get it to go a long distance. Also your putter is designed to give it forward velocity and 0 upward velocity. So it's very interesting. It's also used in firing missiles. For example, you have the short-range missiles generally have these lower angles of attack, but the long-range missiles generally have this very, very high ballistic arc to them. If you get that ballistic arc high enough, the Earth actually rotates underneath your missile, and so you can go even further. And that's the idea behind intercontinental ballistic missiles, which are becoming slowly a thing of the past, which is nice. But it's still kind of interesting that you get the same thing. The most interesting thing about this is the angles themselves. The 2 angles that will give you equivalent paths, as long as there's no air resistance, are always complementary angles. You add them together and they equal 90. So 50 and 75 would work, but also 83 and 7 would work. Or 29 and 51 or 61, right? Will give you the same things. And those complementary angles always end up giving you equivalent paths. Here is an equation that comes from all the stuff that we've done so far, a little bit more. And it is the range of a projectile level ground for which air resistance is negligible, so how far it will go. If you have the angle and the velocity, so this is the velocity, doesn't care what, it's not talking about the x or the y velocity, it's talking about the overall velocity, the angle, and g, right? Those are the only things you need to know. And you can figure out how far it's going to go down range. That is determined by using the equations in the x and y and solving them together. They use these kinematic equations, the x and y direction, and solving them together. Other interesting things that come from this, since our world is not truly flat, is the idea of orbits, right? If you have a tall tower on the Earth and you start shooting things off of it in a horizontal direction, you notice that if you shoot it pretty slowly, it just lands next to the tower. Shoot it a little faster, it lands further from the tower. Shoot it faster still, it lands further from the tower. Shoot it faster still, and it goes way far around the edge. But if you shoot it at the right speed, you can actually get it to orbit. Why is it? Well, orbiting is essentially just falling at the same rate that the Earth falls from your feet, below your feet. At the Earth's curvature curves beneath you. So in other words, this one that orbits is falling 1 foot down for every 1 foot of curvature of the Earth, or whatever. Its falling rate is the same rate of the curvature of the Earth. And that's what orbit is, quite literally. If you get going fast enough, horizontally to the Earth, you are literally just falling around the Earth, but you're falling at the same rate that the Earth is curving. And at different heights above the Earth, the speed that you need to be going is different for that. You have a different orbital speed necessary. The closer you are to the Earth, you have to be going much faster. The further you are from the Earth, you don't have to be going quite so fast. This is actually what they do when they put things into space, like when they used to fly the space shuttle and other things. But now when they fly the Soyuz spacecraft, when they fly, they don't just fly straight up into space. So that's often what you see happening, because that's what the space shuttle starts to do when it first takes off. But it doesn't take long before the space shuttle actually turns, it pitches, and then it rolls upside down, and then it fires its rockets again in this direction, and it goes off in a horizontal direction. And that's true. That's been true for all spaceships. And if you watch the launch long enough, you'll actually see that happening. It goes off in an arc, and then it rolls over and takes off again. Now, let's talk about adding together different things in 2 dimensions. For example, velocities. We're now in a boat on a river. We're crossing the river. And of course, the boat has some kind of power that's helping it cross the river. In this case, it's using some human power. It's a rowboat. And it's moving across the river this direction with this velocity vector. Here's the velocity of the boat. It's directly across the river. The boat. However, the river is moving. So the river is pushing the boat downstream. And it's pushing the boat with a velocity that we call velocity river, which is off to the right there. So what is the overall speed of the boat? The rower is rowing the boat one direction. The river is pushing the boat in a direction 90 degrees to the rower's direction. And the overall speed of the overall velocity of the boat is actually to the right and downstream. Right? It's across stream, but it's also downstream at the same time. So the boat is actually going faster than either the river could push it or the rower could row it. But it's going off in an angle, right? And so you have to deal with that. You have to mess with that. Well, how do we add those velocities together? Well, of course, we break them into components. This one's easy because the velocity of the boat from the rower is all in the y direction. And the velocity from the river is all in the x direction. We've set it up perfectly. So they're already broken into components. All we have to do is take the square of this one, the square of this one, add them together, take the square root, we'll get the length of this one, and then we take the river. If we want to know this angle here, that's the same as this angle. So if you want to know the angle theta, then you take the velocity of the boat and the velocity of the river, take the inverse tangent, and you're done. I mean, that tells you the angle which the boat is traveling down the river.
So that works for velocities also?
It works for velocities too. It works for any vectors. Yep. So you can find the components to do it. However, here's a problem that's not as simple. We have y direction is north, or x direction is to the east, right? And we have an airplane flying along, and it's trying to fly north, but the wind is coming from the north east, so the wind is blowing towards southwest. So what is its overall velocity? Well, obviously it's going to push the plane to the left, and it's going to also push it backwards a little bit. It's going to push against the plane a little bit. But how much? Well, we're going to have to resolve those vectors. The velocity of the plane is easy. It's this one total. It's this one pointing upward straight up to the north, because that's the way the plane is going. But this one here, we're going to have to resolve into two vectors. There's going to be a westward vector and a southward vector. The westward vector is the one that's pushing the plane off to the left. The southward vector is the one that's making it not go as fast in the forward direction as it wants to, or the northern direction as it wants to. So it's getting pushed against slightly. And so we're going to have to resolve that into two vectors and then add it to the velocity vector of the plane to get our original. So in the case of the boat, here they do this. They show that the velocity of the boat is all in the y direction, and the total velocity is going to just be velocity of river plus squared plus velocity of boat squared, total velocity 1.42, and that's great. The direction, inverse tangent, 70.75 over 1.2, that's easy peasy. But the airplane, a little tougher. We're using the same thing here, and with the airplane we have to see that we're going to do something else here. It's going to be the same process, just going to be a little bit more work. We need to, first of all, recognize that we have an x direction and a y direction for the velocity of the wind. So it's going to include two parts, and that's what they're doing here. So the velocity total in the x direction is only going to be from the wind. The wind is the only thing pushing this thing side to side, because the plane's trying to fly north. But the velocity in the y direction is going to have two parts to it. The velocity of the plane and the velocity of the wind are going to be added together. The velocity of the plane, of course, is upward, which we call a positive number. The velocity of the wind is going to be downward, which we're going to have to call a negative number. We'll get to that in just a second. But let's do, right? So the wind is going 38 meters per second, they say. Is that right? Is that what they said?
Yes.
And the angle 110 degrees, and we get negative 13.0 meters per second, which is pushing it to the west, right? That's fine. Now, velocity total in the y direction. Velocity of the wind, 38 meters per second. Cosine of 110 is negative 3.42. No, I'm not doing the right thing yet. That's velocity of wind in the x direction, which we just calculated. That's what it is, right?
Now we're doing.
Okay, velocity total in the y direction. Here they have a typo. That's why I was looking at this, because I was trying to figure out what this is. This typo is velocity total in the y direction should equal velocity of the wind in the y direction, not in the x direction.
Okay.
Plus velocity of the plane, right? So here we're calculating the right thing. They just put it wrong right there. Velocity of wind in the y direction is 38 meters per second times the sine now of 110, which is 0.940, and then we have minus our 48 meters per second, or sorry, minus our 45 meters per second, which is this should be plus. Now, the wind is down. This should be up.
That's the wind. That's the wind on the y-axis. That's what we found it. That's pushing us back that far.
Right. I'm just trying to figure out where the numbers are coming from. I didn't read them very carefully, so I should go back and read them really carefully, really quick.
I think we're supposed to use that number. We should still use.
So velocity of the plane is 45 meters per second up. Velocity of the wind is down, but their angle they're taking is 110. Okay, so I know what they did now. Since they're doing the sine of 110, they're finding this side, but it's going to give them a positive number, and so they've just flipped the two numbers to get a negative. And that's bad mathematics in my opinion.
They do that a lot.
Yeah, it's unfortunate, but there are different books that do different things, and I've forgotten that they do this here. So what they did is they took the sine of 110, what you really should do, and you can do this any way you really want to, but what you should really do is take the sine of this angle here, no, the sine of this angle here, and that would give you that negative number. They're taking the sine of this angle here, but whatever. I'm not really sure why they do it that way. People do different things, but you should recognize that it is a negative vector anyway. And when you recognize it's a negative vector, you can just put the 45 and subtract the other one, and it's just negative. But anyway, point being is that they get the answer one way or the other by observing, right? This is essentially by observation. They know it has to be negative. So that one's going down. Negative 9.29 meters per second for the velocity of the wind in the y direction, right? Once you know the velocity of the wind in the y direction, then you can actually calculate the total velocity of the wind. Oh, I see what's going on. I'm reading this problem wrong. They never gave us the velocity of the wind. They gave us the total velocity of the plane. They gave us the airspeed of the plane, essentially. That's what it is. The plane is known to be moving 45 meters per second due north relative to the air mass. Well, its relative ground velocity is 38 meters per second. Okay, so the 38 meters per second is the velocity, is the total velocity. The 45 meters per second is actually the velocity of the plane in the x direction.
Okay.
They never gave us the velocity of the wind. They're using this to calculate the wind. So that's the difference. That's why it's different.
Okay.
But anyway, you can see here that they're breaking it into components, and that's the important part. Let's see, where were we? Here we're right there. So this 38 meters per second here, it works in the x direction because the wind is the only thing in the x direction. It doesn't work in the y direction because we have to take the ground speed and the air. This one is the air, the relative to air mass, and the ground speed, and then take their difference to calculate the y direction. And that's why they take the difference. Does that make sense? So essentially, this one right here.
Yep.
This one right here is telling you how fast the plane is actually moving relative to the air this direction.
Okay.
So relative to air, meaning the air is moving one direction, the plane is moving the other direction, right? This one is the speed that the plane is moving relative to the ground.
Okay.
And the wind is the thing that makes the difference between relative to air and relative to ground.
Okay.
And so you have to take the difference between them. You know you have to take the difference so that it ends up negative because the wind is slowing it down.
Pushing.
That's right.
It's pushing it.
Right, and so that's why they do it that way. And of course, this one is a component with that sine of 110, and that's why they did that way. So anyway, sorry to confuse you on that, but that is that's kind of the reason that they actually do it this way is because this is the way pilots. This is the information. Sometimes this is the information pilots can have. Most pilots will not know their ground speed. They'll have to calculate that, and so
That's what I thought.
that would be it confused me a little bit. They would give you the ground speed. Usually, you have to calculate the ground speed. You get the air, you know your airspeed, and you know the wind speed, and you calculate your ground speed.
Because it's easier ways to calculate the wind speed, isn't there?
Well, and the reason that they're doing this way, I assume, is because a lot of pilots use GPS now, which gives you the ground speed.
Oh, okay.
So when you're using GPS, you know your ground speed and you know your airspeed, and you can calculate your wind speed.
Okay.
The only other way to know your wind speed is to actually get on the radio and ask it,
Yeah.
what's the wind speed in this area? And they'll tell you, and you'll have an approximation.
Yeah.
So, I actually just finished ground school for pilots.
Nice.
I probably will never get my pilot's license because it costs too much. Anyway, the breaking up of the components is important. Is that making sense, how they're breaking this into X's and Y's and doing things separately? It can be extremely confusing because there's so many numbers, so many equations. And so what I always recommend people do is to split the problem, and sometimes even just split your page down the middle and say, this is my X side, this is my Y side, put all the stuff you know for the X direction in the one side, and all your stuff you know for the Y direction on the other side, and literally work them separately, even if they're side by side. But work them separately. Some people like to do one and then the other, like they kind of do in the book. But I prefer to kind of have them left and right side of the page. It separates them better for me, and it also helps me to see the whole problem better. But it's just up to you. But I definitely recommend you physically separate them somehow. Let's see if we can find another problem here. This is a good one because it's a little simpler in its understanding. An airline passenger drops a coin while the plane is moving 260 meters per second. We assume that means forward at 260 meters per second, right? What is the velocity of the coin when it strikes the floor 1.5 meters below its point of release, measured to the relative to the plane and measured relative to the Earth, right? So if you measure relative to the plane, is the coin moving relative to the plane side to side? No, it's only moving relative to the plane up and down, right? So it's just going to fall to the bottom of the plane. It's just going to be a normal kind of dropping a thing problem, right? Measured relative to the Earth, however, it is moving 280 meters per second forward and accelerating downward, right? So part B is the really interesting part. In part A, we use one of the kinetic equations. We find that it moves at 29.4 meters, or sorry, it moves at, when we solve that, it moves at, there we go, 5.42 meters per second. It was a squared thing before. You can see that there was a meter squared per second squared there.
Yeah.
And I had to wait for them to take the square root. So they take the square root and it moves at negative 5.42 meters per second after you drop it 1.5 meters. That makes sense. We can accept that. But what happens if we're moving also 260 meters per second forward? Is that what it says?
Yes.
So 260 meters per second forward, well, then you have the triangle where you have a small 5.42 downward velocity as one side of the triangle, and then you have a 260 forward triangle that that kind of finishes off that triangle. And I should draw that triangle for you, but I didn't.
So you use the two vectors.
Yeah, so those become your two legs of your right triangle. Add them together using Pythagorean theorem. Square of 260, the square of negative 5.42. Add them together, take the square root. Turns out that it gets 260.06 meters per second. It's just a little bit faster than the plane. Well, of course that makes sense because the downward motion is just a tiny motion compared to that 260 forward,
Yeah.
right? So it's just a little bit faster than the plane relative to the Earth, and you're good to go.
It is pretty fast now.
And then to find the direction, you of course are going to use the angle formula, tangent, inverse tangent of velocity in the y direction over the velocity in the x direction. Turns out to give you negative 1.19 degrees downward angle as it's traveling downward. That actually finishes the chapter. Are you kidding me?
Really?
Yeah.
Well, I have some questions on the homework.
Good. We got time. Oh wait. Yeah, that's good. Okay, well that's good. We can live with that. Let's do some homework.
There's 3 problems I pretty much got stuck with.
Okay, I'm going to do the homework on educreations here. And I'm going to go ahead and stop this recording before I run out of space.